I never totally know. Okay. Well, okay. Oh, good. It looks nice and even. Okay, finally, for once. Hey, hello, everybody. Welcome once again. We are what? Can we believe we're already at week 7 now of
Wait,
this?
what?
Yeah, this is the 7th week we've been doing this here at this channel. This is Learn Math with me, Brian Sapinski, and Brianna here once again. You could slide yourself in a little bit more. So, chairs clanging on a hardwood floor, folks. Yes. Okay. So we're ready. We're ready to do this once again. Brianna's still in the middle of lunch here. She's waiting for her soup to cool down. her and her mother, they are soup fiends or whatever. But then again, I used to be a soup fiend myself for a good number of years, but I'm not as reliant on it as you are over there, right? Yeah, pretty much. Okay, well, I hope you're enjoying whatever. Well, it is, of course, yeah. So, well, I hope you're enjoying whatever you're having for lunch, and that you came here to get some math help. You know the deal. You know where you're at right now. YouTube.com/Sapinski Math. The live chat is right here, waiting for anybody that happens to be dropping in and get your topics submitted right there in the live chat, so I could see them. Get yourself working there, or if you feel more comfortable with sending me a direct email, brian.sapinski@gmail.com, please do so, and we will get the ball rolling for you. So that's the nature of what we've got going on here. What? I'm asking if any of my friends would, if there's any topics they wanted to suggest. And one said fractions using Pokemon.
What?
How? Mind telling me? Oh boy. So sometimes I occasionally look for pitches before we get started, and I get weird stuff like this.
Remember that
I'm creative. I'm not necessarily sure I'm that creative sometimes, but I do have a puzzle that I want to.
Remember that one time I gave you an equation from a video, and you're like, "No, I can't do that."
Yeah, I probably still can't. Remind me later what the heck it was.
Remember,
But anyway, no, wait, not now.
Take the worst thing that could happen to someone and multiply it by earthworm. That's what earthworm Sally is feeling.
Yeah, that we can't do. Again, they're obsessed. It will never die, folks. Okay, all right, let's get to this here. Okay,
just
puzzle.
me and Gianna.
Okay, I got you. Okay. Yes, I got.
Sally.
Okay, enough. Okay.
Diseases
All right.
from Florida to Cali.
Okay. Well, let's see if in this puzzle if we can minimize Earthworm Sally's path of destruction here or whatever. Okay.
It's sadness.
You know how in the past. Okay. So on some of our previous live streams, we showed some problems that you were seeing with networks such as these, where you've got a series of vertices, hubs, whatever you want to call them. We have them all connected by a series of wires, edges, again, whatever you want to call those, and things like that. Here's the challenge I want for you, Brianna. Okay, and for you guys out there, I want you.
It kind of looks like you can stick your hand in it, but also no.
No, but that's not what we're trying to do. And here's the challenge I pose to all of you guys watching as well. Here's what I want you to do. Right now, start by, okay, how many different vertices, how many different network points do we have here in this diagram at the moment? How many do you count? I'm just making. Wait, I'm just making. Okay, well, take that. Okay, so how many vertices do we got?
Can I use the blue one so I can mark it?
Well, wait. Don't mark them because it's going to be important. I'm looking for the vertices, the actual points themselves. Come on.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, all right. So she counts that there are 14 edges. Okay, now you can see that there are many different connections that that this has right now.
and several points are connected to multiple other points in different fashions and stuff like that. But here's my challenge to you right now. I want to remove several of these edges, a lot of them, in fact. But throughout it all, I still want the graph to be connected, okay? Your object is that you want to remove as many edges as necessary so that all the points in the network are still connected using the fewest number of lines and edges possible. Okay, so I want you to just start here, take our rag and just start rubbing out edges or whatever. Okay, and try to make sure.
Edges?
Yeah, just erase as many of these lines as you can while still keeping
the general shape.
But while still keeping all of the points connected in some way. And see what you come up with too.
All of the points still connected.
All the points still have to be, all 14 of the points still have to be connected in some fashion. All right, so if you take away that, okay. All the points are right now still connected. As long as I tell you that you can, keep going,
Points are.
You can still get to them by going around. That still counts. Go ahead, yeah. But you understand now what you're looking for? Do you guys understand what you're looking for out there? Okay?
I don't know if I should erase these. This.
Huh?
This one?
Go ahead. Everything's still connected. As long as I tell you you can keep erasing, okay? You can still do more.
Can I keep erasing?
Yeah? You're still good.
That's where I'm gonna stop.
You can keep going. You can still erase more. Go ahead. All right, well, take a couple. Sure. Go ahead. Okay.
They're all still connected.
Everything is still connected. Here's the, okay, here, I'll tell you what. Back away for 1 second. I'll explain a little further what I mean and see if you guys spot this as well. The idea is in spite of what she's erased right now, the key here is that there is still a way through the remaining edges for you to get from any point in the network to any other point in the network. Do you understand? Okay. Now, so like for instance, even these 4 points in the middle that you have now made a dead end at, you could still get to any of the other 13 points in the network. You could make some kind of a path from any point to any point still. Okay, now I'm going to tell you now, you can still erase more lines. Keep going.
Really?
Yeah, you still can.
Can you erase this one? This line?
Go ahead. You're still good.
And
as a matter of fact, you know what? You can stop. You can stop now.
Yay!
Okay. Because now I'm going to tell you, if you erased any more lines, you would be at a point where you would disconnect some of the points in the network from the rest of the points in the network. So that one last one was the one you needed. Okay? So that's the deal. Okay? Now, here's what I want you to see. Okay? This is everything that's here. When you have a network such as this, Brianna, where you have the minimum amount of lines that connect every point in a network to each other. This is an example of what is referred to as a network tree. Okay? Now, here's the next thing that I want you to see within this puzzle. Okay? Now I want you to actually count how many lines you left behind, or as I've been referring to these in the past, edges. Okay, how many lines? Again, any connection between two direct points, that's considered an edge.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I count this one?
No.
11, 12, 13.
Okay. You have 13 edges in the bit. Okay, so you've got that. So now my question to you is, okay, all right, so here. You've established that, okay, in this grid of 14 points in this network, you found that the 13 edges that you left behind made them in such a way that they constitute a tree. Okay, keep that in mind. What about, okay, so let me draw a new network, okay, and then I want you and you out there to do the same thing. Make a tree out of this, okay? So what if
Oh gosh.
okay? So same story here, okay? For this one, how many vertices do you see?
8.
Okay, see 8 vertices. Okay, all right. You got a bunch of edges there. Again, do the same thing. Make a tree out of it by erasing as many edges as necessary until the graph is minimally connected, where every point is still connected to every point. Like I said, there's a lot that you can eliminate right now. Okay, get rid of that one. Sure, go ahead. Right up. Okay, everything is still connected. Again, like I said. Okay, yep, no, keep going. Don't worry about how many dead ends you make. Just keep going. Yeah. By the time you figure this one out, you're gonna see. You're gonna be able to see something. Okay. Sure. Yeah. No. Keep going. Again, fewest number of connections possible. Okay. As long as you see that every point still has a way to travel to any other point, keep erasing. Keep erasing until it's not possible anymore. Okay. Getting there. Getting close. Closer still. Can you erase any other points and still? Can you erase any other edges and still get a connect? Make a path from anywhere to anywhere. Okay. If you erase any more, okay, and she hands it over, and she's correct. She is done at this point. She has successfully made a tree again. Because again, erasing any more edges at this point would disconnect something from the rest of the network. Now, one more time, count how many edges you left behind. And at that point, we're going to be able to establish a pattern. You counted 7 edges. Okay. Compare this with the first one that we did. Okay. What do you notice? What's the pattern you notice between the first one we did and the second one we did?
They're like one number under each other.
Well, what's one under what?
The vertices are one over the
number of edges. Okay, and that's the way it's supposed to be. The whole idea is, Brianna, and I'm going to put this back so that you can see it. The idea here is that, like I said, with the way these vertices are right now, the idea is that no matter which point you start from, you still have a legitimate path right now that could get you from any point to any other point in the network. But there's only one possible path. So, like for instance, if you wanted to get from here to here, okay, there's only one path you could take to get there.
Oh.
Yeah, that's where you come in to say what the path is.
Oh god.
Yeah, and that's the only way you can get there. Now the thing is, had you not eliminated all of the lines that you did, okay, what would happen was, like, even if there was just one more line or one more edge in the thing, even if there was one more edge right here, that creates, within some of the points in the network, it creates a closed circuit. And that thus means there's more than one way to get from here to here, either this way or this way. And a tree cannot have that. A tree has to exist in such a way that it minimally connects everything in the network. And what you're going to see is that as a general rule, for however many vertices you have in a network, the number of edges will always be one less. That guarantees the minimum connection. So that's essentially how a tree works. And from the way that this looks, now, okay, you make your joke with regards to like we talked about factor trees, I think, in a previous thing, and we've gotten to all the branch drawing business and stuff like that. Okay, you're saying, okay, this doesn't look much like a tree. Okay, let's make it a little more like a tree. Let's suppose. Okay, well here, let's name the points briefly. Okay, A, B, C, D, E, F, G, H. Okay. So, because you could do this if you want to.
No, it can't be point E. It can't be point E. I have to change something.
Why? Why is it not E? Uh-oh. Should I be prepared for something, folks? Oh, you stop that! Her with the earthworm again.
It's not point E. It's point earthworm. It can't be point E. It has to be point
You stop
earthworm.
that.
No! Why can't it be point earthworm?
The virus must be contained.
What?
Anyway, all right. So we
don't know if earthworm salad carries coronavirus.
Let's make this a little more tree-like. Let's establish one of the points. Suppose point A. Let's establish that as the root of the tree. Okay. What I want you to do now, Brianna, and you guys try it out there too, is seeing how this network tree is drawn right now. What I want you to do is I want you to draw additional branches, draw the additional edges and whatever and stuff like that.
I'm making a tree.
Do it here.
Oh.
First redraw all of these edges and stuff like that using point A as the root. Connect everything to point A as you see it right now, but have it branch upward the way a tree would normally look. Okay, well, wait, make the dot and establish what letter it is. Make sure it matches what you see here. Okay, sure. And if anything extends beyond those, keep going. Now, wait. Do you see a direct connection from A to C?
Oh, no.
Yeah, okay, so you can't call that C. Wait, you can still draw wait. Move over to the side just a little bit. Okay, there you go. Now you got it. Yeah, because it has to match the details that you see here. Okay. Here, just slide over a little bit so everybody can see what you're doing. Okay, she's good so far. So you see how she's redrawing it here?
Yeah.
Okay, all right, what else? What else is A connected to?
I have to stand back.
Okay, wait, no, it's okay. All right, what else? All right, what else is A connected to? Wait, read the actual grid itself. What else is A connected to?
K.
Huh?
K.
That's F. Sorry, I fixed that. That's F.
That was F.
Sorry. Have you gotten used to our chicken scratch, folks? We are always committed to bringing you the best math content that we can to help you. Yeah, exactly. There's a reason we teach math, folks. No, but she's usually good with hers. I just, for the sake of me trying to speed things up or whatever, Well, here, wait. Let's do this. Wait. Think of it in perspective of a normal tree. Here, wait. Establish the F dot right there. Okay, all right. Now branch up. Go upward. Well, it doesn't have to go that far. Okay. Okay, and what's point is that? That's G. Okay, here we'll just slide. Okay, and then you have one dot for will you stop?
Earthworm. When it has to be point earthworm. Okay.
And you're missing something. Okay, sure. I would have probably preferred you sent it that way or whatever the case is, but all right, that's fine. Okay, and there's the root. There's the root of the tree. And wait. At least get a green. There is your network tree. Yeah, that's all of them. And there you go. Our network tree is complete. All of its branches are in place there.
We don't need point earthworm because guess what's in the tree?
Oh.
Earthworm Sally. It's Earthworm Sally.
That looks like the tree's got an ugly thumb or something.
Oh yeah. Wait, I'll fix it.
Hey. What are we gonna do here?
You
All right, what do you get?
Earthworm Sally is ugly.
No. I
Yes.
just said it looked like a thumb. So who knows there? So all right, but you get the general idea then of how the trees work and stuff like that. So it still plays on the idea of the network, but now we're getting out of all the circuit business that we talk about with Eulers and Hamiltonians and all that other business or whatever, and you're just looking for the minimal possible way to connect for everything to have a path to everything else.
Ooh.
And that's how a tree traditionally looks with its branches. You get from one branch to another, you work your way back down to the main root and connection and work your way up elsewhere. So that's the nature
Sally wants to role play with this apple.
Don't start. Okay. All right. Do not bury the joke. Okay. We've gotten where we
so we can role play.
Chill.
We can all play.
Rana.
And this is Earthworm Sally saying this.
Okay, yeah, but it's coming out of your mouth, so.
Dude, this is what Earthworm Sally said.
No! Yeah, but you're still the messenger, though, so you gotta chill with that.
Earthworm Sally!
Oh, what are we gonna do with you? So, anyway. Okay. All right. So we got a little because we didn't do any discrete content last time. I realized that, so I wanted to get that in for the last couple things because that was something that my discrete guys were working on last week. Simple enough concept as long as you're good with manipulating graphs and connections and things like that. And it's a good puzzle for yourself. You can actually from those trees make a lot of different. Trees out of the connections. The one main thing you just want to make sure of is that no matter what, as you look at those, to ensure that you have the minimal number of connections, you want to just make sure that there's no group of points that have lines connecting them that form any kind of closed figure, or as we call it, a circuit. As long as no circuits exist and that there's only one possible path to get from any point to any other in the network, then you have a tree and you're covered. Okay, so hope that makes sense and stuff like that. Okay, we'll leave it for a minute here. All right, okay. While we're on the subject of trees and everything and stuff like that, here I'm talking about week 7, and here we're talking about trees. But so.
Dang it! I thought you were gonna say now that we are on the topic of earthworms.
No. Okay. We brought up somebody was bringing up the whole thing about somebody was bringing up the thing about combinations and they were talking about tree diagrams and stuff like that or whatever. I don't want to necessarily talk about those kind of trees, although maybe I do because something that you were asking me about, like the choose your own adventure thing or whatever. I thought about it. I thought about it after we were done with that live stream, and there is a circumstance where, in terms of doing those possibility combinations, where hold thought a second. Wait, hang a minute.
The Choose Your Own Adventure thing on Netflix I'm thinking of is the new Carmen Sandiego one, or the
No, I know.
New. It came out a while ago.
Right. No, I understand.
Like I'm thinking of that because, like,
okay,
I know on the first choice, the second choice. So in like the second instances where you gotta choose what.
Why don't you come in and talk to them?
Okay, so like the second instance where you gotta choose what Carmen does. So like the first one, like
So we started scenario A. All right, there's 2 choices at the beginning.
So like it's like this choice. So wait, here I'll make it.
We'll treat
So this choice and this choice, and they both lead to basically the same scenario.
Okay, or they could. Now
they do lead to the same scenario. and then one of them like would end the story right then and there. It's like I don't want to spoil it for anyone who now wants to watch it, but like one of them, it ends it right then and there, but the other one keeps going.
Okay, well, all right. Well, that's not quite what I'm. Okay, from that circumstance, in terms of doing the combination calculations and things like that, and counting principle, that would not apply exactly to a scenario like this. Here's the only way it would work. Well,
there's always something that would end the story.
Right. Well, that's the idea, and the idea that some branches, based on your choices, could carry the story for longer than others would. However, okay, that in terms of accounting principle calculation, that would not work for the kind of stuff that we're doing here. The only way that a choose your adventure type scenario would truly work for the counting principle and the number of outcomes from a basic level standpoint, from an elementary and high school level standpoint, would be in circumstances where, okay, you start at the top, you have two decisions, and every time you have to decide, you have two decisions to make again. Now, in some cases, okay, sometimes when you make the second choice, they lead to their own paths if you continue along one option or another. And in other cases, if you do decision A and then decision B, or if you do decision B first and then at the two choices there, that choice leads you to the same outcome as this way. Okay, that's different. Then we got something here that we can work with. But even then, it would only work if you have if no matter what choices you make, the story automatically ends after you have performed a specific number of choices. Okay? Yeah. That's the idea.
So if you choose I kind of have to say something.
Okay, wait, hold on. So here's the issue, okay? So and I think, wait, listen. And I think you remember several weeks ago when we had the Kubert pyramid up, do you notice how it starts to look
like it?
Because it is, in a sense. Okay, I didn't put as many levels on it, but here's the idea. Okay, it would have to play out like this, and you would have to see it from a combination standpoint there, because okay, the idea is on this level of the pyramid, you have combinations where you've made one decision. You've made one decision, and the idea is this is option A, this is option B. Okay, so the first number in the combination circumstance is the number of again, as Pascal's triangle shows.
Can I
okay, possibility, going to the left is choice A, and we're identifying how many times did we how many ways is it possible where out of so many decisions we pick choice A versus choice B. We're going to have this number, the R, represent all of our B choices. Okay, so the idea is just right there. Okay, represents all of our B choices. So the idea would be that A would represent 1C0, which, okay, how many times out of 1 did you pick choice B and lands right here? You did.
Well,
there's only one way it can be done. So that calculation's what there. Versus,
can I read the description of the
thing? So you have one way you could land here and one way you could land there.
Can I explain what the basic story is from the description of it?
No. We don't need that. That's irrelevant to the conversation right now.
Because one of the choices, in order to explain it.
Brandon, you're missing the point here.
Okay, so
Brandon. Whoa.
When you get to the second choice option, there's a thing
all right,
where
so now you've made two. So now
there are
two choices.
So one of them is go with.
So here,
just
So here at the first,
wait it out, or just like do it right now.
Okay.
And if you choose the do it right now option, it leads you to the end of this.
Okay, but again, that doesn't fit. But that does not fit this model.
It's like,
okay. Do you understand?
Ends the story there.
Brianna, but you're missing my point though. You're sticking to your guns on this, but from an elementary model, that does not fit this. Where some branches ends early and others keep going. That does not fit this.
It doesn't?
That does not fit this model. You have to, no matter what choices you make, you have to end. The story has to end after the same number of decisions, no matter which way. It can't be that some stories end after you making only 2 choices and other stories end after you making 6. It doesn't work. That would not fit this combination model. Okay, it has to be that. So, like with the way I've set this tree up, you see, Bria, the idea is that no matter what you do, okay, no matter what decisions you make, you're still going to make 4 choices no matter what. Because to get from top to your ending on the bottom, you have to make 1, 2, 3, 4 choices. 1, 2, 3, 4 choices. 1, 2, 3, 4 choices. No matter what way you go from top to bottom, it takes you 4 beats. You understand?
Yeah, but like.
But that's the idea of mathematically how you can apply a counting principle from an elementary standpoint to those choose your own adventure things. It's a guaranteed set number of decisions, no matter what choices you make. The question is, how many ways can you trace your way down from top to bottom to get from beginning to the end? So for instance, Brianna here, so take a look. So after making one decision, there's one way to get from the top to here, and only one way to get from the top to there. That fits the calculations of 1C0 and 1C1. Now, how about after you make 2 choices? Wait, Brianna, you got to stay here and look.
I am.
You have to, okay. Okay, now after you make your second choice, there's 3 places you can land, but the question is, how many ways can you end up at those 3 places? So how many paths are possible if you never choose option B? How many paths are there possible from the top down to here? How many ways can
3?
Wait. This is path number 1. Can you go downward any other way from here to here? You can't. The only way you get here from the beginning is to choose option A every time. So there's only one path. There's only one path from the top to there. You're not going down and back up. You know, you can't see. Remember, everything here is strictly moving downward. You know what I'm saying? So same thing over here on the right side. You made 2 decisions. You chose B twice. How many straight down paths are possible to get from the top to here?
2.
Wait, where's the second way to do it? You're not counting edges. You're not counting edges, just the full path. There's only one path. But what about here in the middle? How can you get to this middle point from the top?
Like something like this. Like you could choose either one of these points and then go to the same thing.
Right. You choose option A, then B, or you choose B first, then A. So there's 2 ways to do it. So you chose B once out of 2 times. Okay, and then follow this. Okay, so at the next level, now you're making your 3rd decision. And depending on whether you chose option B none of the time, once, twice, or all 3 times. Let's see how those go. Again, Brianna, at the ends, Brianna, how many ways are there to land here or here from the top? Again, there's only going to be
2.
No.
Oh, 1.
1. Yeah, 1 over here and 1 over here. And that's going to continue down the sides no matter what. Even when you get, no matter how many levels deep you get into the mix, there's only going to be one way to get to those. Okay? Now how about the ones in the middle? Here, choosing the B option only once. to get from there to there? Can you see it?
Hmm?
How many pathways trickling down from the top to here? How many pathways down can you find? Let's see what you go this way. That's one option.
And then
Zigzag it. That's two.
three.
You can do a third. Go to the right first. It requires one move to the right and two moves to the left. And there's three ways to do it. And think about this, Bria. If there's three ways to turn right once, how many ways do you think there's going to be to turn right twice? Brianna, yo.
Double?
Look. If there's three ways to come down this way, how many ways do you think it's three again?
That was double.
No. Don't confuse the. It doesn't suddenly become a multiplication of the things there. Okay. So here I'm going to circle those to the top, and I'm going to put one at the top because there's only one way to start and finish at the top, and that's to not go anywhere. So we got that. That. Okay. And then your fourth and final decision, let's see what everything comes out with here. Okay? Over here on this side, Brianna, to get one, to only move right once, to get from the top down to here. See how many pads it takes. So we know here's one path there.
Three?
Let's see. Here's one path. Here's cut early. That's two. Cut even earlier. That's three. Four. Cut right at the beginning there. And if there's four here, if there's four here by only choosing option B once, what else are you going to see? If there's four over here, Brianna, quit nursing your drink for a second. If there's four over here,
there's four over there.
At the three option, okay? Choosing the B option three times and the A option once. There's four different spots where you can pick the A. And now the fun one's in the middle with 4, 2, okay? I'm going to give you a hint without having to physically try to find all the paths, okay? Do you see like this? Do you see like this 4, for instance? If you look at the two paths that came from directly above it, look at what numbers are here. How did these numbers connect to that number? How do 1 and 3 connect? They add.
That means it's 6.
You got it. It's 6. And as you go from level to level, every further branching down of Pascal's triangle will continue to follow that path. So the next level, which will have 6 numbers on it to represent all of the combinations involving 5 items, will start and ends with 1s, and all the numbers in between will have the additions of the 2 numbers that came above it. It'll consistently work all the way down the track. So Brianna, 1 and 4 would make 5 at these ends, and in between you have a 4 and a 6 to combine, and they'll make 10. And it continues from there. So, and all these, if you were to perform the different combination calculations that we've discussed before in previous streams or whatever. So like, for instance, to calculate 4C2, we said that was based on the bottom, you count from 2 all the way down to 1. There's 2 digits there. So you have to start from 4 up here and count down for a total of 2 digits. That would be 4 times 3. 2 times 1 is 2. 4 times 3 is 12. Divide, and there's the 6 that we got right there. I can't draw an arrow. And for any of these others, the same thing applies. So that's how it works. So that would be, you could do a combination tree diagram like that using Pascal's triangle and things like that. But even then, again, the conditions are that for some type of choose your own adventure type of thing, every decision is a this or that. Every decision is a 50-50. And no matter what choices you make, the story always ends after X number of choices. Get it?
Yeah.
So that's the hook.
But
Okay.
definitely not in the Carmen Sandiego one.
No, I understand that. Okay, but the point is from an elementary standpoint. That's from an elementary standpoint. That's how you would have to. That's how you could calculate possibilities under that type of circumstance. You know what I'm saying? So that's the whole hook of it. All right. So that settles the issue from a couple weeks ago about that type of tree or whatever. Okay. But now let's take things one little step further. Let's stay in the trees. Let's stay in the trees category. Okay. I was before because I was going to get to that. Well, let's keep it. We're going with trees here and stuff like that.
But
okay. Let's go with another type of tree. Okay. And I don't know if we did these before or whatever, but or exactly how I'm going to use them. But here's what I want you to get for me. Okay. I need a number that's going to properly work here. Stuff like that. Okay. I'll start with the basic number. Let's start with the number 50. Okay. Give me a factor tree for this number. Give me two numbers that make 50, and if either or both of those numbers can be further broken down, do so.
25 and 25.
No, wait. 25 times 25 will give you 50?
Oh, no. Oh.
25 times 2 will give you 50. Okay?
5 and 5.
Okay, 5 and 5. And can anything there be broken down further? No. Okay. All right. And just for even's sake, I'll just move this so it's on level with everything else. All right. And I'm going to strike out the 25 because we broke the number down. You'll see later on that there. Okay. We'll just strike out everything from the upper level. There is a reason why, just for to avoid visual confusion with something. I'm going to expand upon this in a minute. You'll see when I get there. Okay. So let's hold on to that. Okay. So, all right, here, let me set that up. Okay, let's try a slightly bigger number here. Okay, how's about? All right, here. Okay, well, here. Maybe not a slightly bigger number, but let's do the same thing. Okay, 48, go.
Is this one dead?
48, go. Okay. We'll cap it. Don't leave it.
24 and 2.
Sure, you can do that. Okay.
Can we split it in half?
Let's branch. Okay, wait. Let's branch. Keep branching.
6 and 8. 6 and 8. I'm going to do something different.
Okay. All right. 6 and 8 it is. Okay. All right. So they both. All right. So they both branch down.
8 can be 2 and 4.
Okay.
4 is 2 and 2.
Okay. So 2, 2. Okay. I'll bring this down.
6 is 2 and 3.
Okay. 6 is 2 and 3. And again, just to even them out. So we'll branch out like that. Okay. So we have those. Okay. And yet still we'll do one more. Okay. Okay. What about? Here,
we gotta chop down this tree.
Not right at the moment.
Get it?
Yeah, I got you. Okay. Let me just find one more number that works. Okay. Well, I'll do a couple more. How's about? I'm just trying to find some other numbers that will fit the narrative. I'm trying to find some other numbers that will fit the narrative of what I want to do here. No, I don't want to necessarily do that.
Yeah, I think this marker is dead.
Okay, all right. Well, I'm amazed they've lasted this long, folks. You know, what I mean, I tried to make a little stockpile for myself. Also, didn't help that you guys were doing so much extra drawing and things like that. But be that as it may. Okay, break down 54.
6 and 9.
Okay, go.
9 can be 3 and 3. That's where it stops.
Okay.
6 can be 2 and 3, and that's where it stops.
Okay, so we got that one there. We'll take out the 3 and 9. Okay, and then one more just to fit the just to fit the final narrative of what I'm going to get into next and stuff like that. Okay.
Oh no, the tree cutter man is coming.
How's about okay? Not yet. It's not your time.
Oh no, the tree cutter man is coming. He has his axe.
Okay, chill.
He's gonna cut down the tree.
Not now.
What?
144. Go.
What?
144. What do you got?
2 and
half of 14.
What?
Half of 14.
7.
Half of 4.
2.
Okay, 72 and 2. Keep going.
2.
Okay, this is odd. So we take off 1. Half of 6.
3.
Half of 12 because you have that 110 left over.
6.
Okay.
6 and 6.
And each of those are
2 and
2, 3, 2, 3. Okay. And bring 2 down. Bring 2 down.
Tree cutter man is interested. Tree cutter man.
All right. So we've done several factor trees. Whoever shot at that like, thank you. Okay, so we've done several factor trees here. Okay, now I want to take things one step further. Okay.
Can tree cutter man do his job now?
No, we're not done yet. So you chill. Okay.
Tree cutter man is sad because you need to cut down the tree.
Stop.
It's his job. You're not letting him
do his job. He's got to let me do mine first. He's encroaching on our turf. Okay. We got a job to do first. Anyway.
This is what he's saying. But it's just a tree.
Yes, but we got to teach first. Okay.
But you need more room.
Noise pollution is a problem. So anyway. Here's where I'm going.
I have an axe, not a chainsaw.
Forget about the sounds of the tree falling. Because the tree will fall. We will be there to see it. So yes, it will make a sound, a very loud sound. So those of you who want to get philosophical with us, okay.
Okay, bye.
I can't even do that. Okay, just go finish your lunch first.
I
anyway.
did, but I did.
Okay.
Here, I'm just gonna stand right here.
Okay, fine enough. Okay, all right. Let me and Brianna finish this, okay? Because there's a point to what I want to make here. All right. Have you up until now, Brianna, when you've been doing multiplications, have you gotten into the concept? And this is the part that I'm wondering about whether we did this in a previous stream or not. And if we did, fine. There's no shame in doing it again because I'm sure people will have questions and they may find this one. Have you so far, when you've been doing multiplications, have you discussed the concept of square numbers yet?
Square what?
Square numbers.
You might have. I don't remember.
Okay, like for example, if I ask you, what are you doing?
Oh, no.
She's writing all over the floor here. If I ask you, for instance, to calculate, let's say 4 squared. Okay. How much is 4 squared? Or let's put it this way. From our previous conversations, Brianna.
16?
Okay. How can you rewrite 4 squared to back up that claim? 4 times 4. You're right. Exactly. That's the idea of what makes a square number. That's second power, which is saying that you have that.
The tree cutter man forgot he still had a same.
So what it means is anytime you multiply a number by itself. Okay. Now here's the thing. Here's the thing. The fact that you multiply a number by itself, Brianna, means you have how many of that particular factor? As the you have 2, and the exponent indicates such. Okay.
Yeah.
So, knowing that, here's what I want you to find in all of these factor trees that we just did a minute ago, Brianna. Okay. Go through each one and identify for me anywhere you see exactly this. 2. This is where you have to look. 2 of the same factor. Look at the numbers that we ended up with in each of these factorings of these 4 numbers. Wait. No, not the number 2, Brianna.
No, wait, there's always 2 factors.
But understand, they broke down further. Look at the ends of our factor tree. Look at when we finished everything. I want you in as many places as possible in this set, and this set. Find as many times where you see 2 of the same factor showing up. Okay? So like in this group, where do I have 2 of the same factor?
2 5s.
Okay, the 2 5s. Okay, how about over here? Where do I?
2 2.
Okay, now
And another 2 2.
There's another 2 2s over here. Okay, don't worry that they're not next to each other. A pair is a pair, no matter where they fall from the tree. Okay. Yes, draw some pairs in the tree. Now that I've said that, we must put some pairs in the tree.
I already draw a pair.
Juicy Anjus, if you will.
Huh?
Anjus, my favorite type of pear. Seriously, juiciest fruit you will find anywhere. So good.
Even juicier than juicy fruit?
The taste is gonna move you. Anybody remember that old advertisement?
Huh?
It goes back to when I was a kid.
This is weird.
That was their old slogan. Okay, all right.
This tree has dropped apples and now is growing pears.
Yes, it is a very hybrid tree. Okay, pears here, Brianna.
It's a juicy fruit tree.
Brianna, pears here. What do we got?
Wait, which one?
Pears. This one. The factors of 54. What do we got?
The 3.
Okay, so we got that. And how about down here? How about here with 144?
2 of the 2s and 2 of the 3s.
Wait, there's those. What else you got?
The 3s.
All right.
And then the 2s.
And then another pair of 2s.
This looks weird.
Well, that's just the way it.
Wait, if you add like this, it looks like 2 Lego hands holding. Looks like 2 Lego hands.
I can think of some other blocks, but that's
like
beyond the point.
2 Lego hands holding each other's hands.
Okay, so we talked about square numbers. We talked about finding pairs in our factors here.
Wait,
and here's now why.
Type of pear again?
Anjou.
No, that's Anjou pear ice cream. That's Anjou pear ice cream.
Maybe sorbet. I don't know about ice cream. I'm not sure that would work.
Sorbet in a cone.
I'm not sure that would work in a milky base. Even sherbet wouldn't apply. I've never heard of pear sherbet or whatever. I hope have any of you.
Well, this is fictional, so it's Anjou pear ice cream.
Moving on.
Or
how about Rita's ice?
Yeah, Rita's.
God, we miss Rita's, don't we?
Yeah. Okay, so I have to change.
One of the few frozen treats that gives me brain freeze. But anyway, okay.
Do koalas give you brain freeze?
Back on point.
Do they?
Here's now why I was looking for all these pairs of factors.
Okay, now it's a cup of
Okay,
Rita's.
now, okay, listen.
Probably shouldn't be looking at, but
listen. Here's why I wanted you to find all those pairs. Here was the purpose of this. We talked about squaring.
All those pairs.
Here's what we talked about squaring a number up until now. Okay, what if you were going in reverse? What is it if squaring a number gets you from 4 to 16? What is it called to get from 16 back to 4? If going from small to big is squaring. Don't worry about it.
Okay. I don't know.
Okay, that's what's referred to as a square root.
Four
would be the square root of 16 because you need 2 4s to make 16. Now, the common symbol for a square root is this symbol. Okay?
That looks like a division sign.
Almost. It's a play on the division sign in a sense or whatever. Okay? We call this the square root symbol, or as it'll be very frequently referred to when you get into higher levels of math, Brianna, this is what's called, it's also called a radical, okay? And no, it is not called a radical because it is officially endorsed by the Teenage Mutant Ninja Turtles, okay?
Wait, I think there was like this one question on the impossible quiz. I think, what is the square root of onion? Or onion is the square root of?
I don't even know. I'm not even going to entertain it right now. But anyway, but here's the point of the whole thing, though. Okay, the idea is, in order to be able to calculate the square root of any number, Brianna, you need to be able to find a pair of the same factor within that number. Okay, so for instance, now as you look at all of these, though, as you look at all the factors, Brianna, look very close. Look very close here.
Oh yeah, here it is. Question 6 from the impossible quiz. It was a bit.
And what does it say the answer is? Lee,
I think
you just love derailing this whole thing sometimes.
I think it was shallot.
Okay, well, let's move on and get to the ones that we actually can get a simplified answer for. Because here's the thing, Brian. We found all of these pairs. Brian, you gotta look here. Enough. Come on, we gotta wrap this up. In all of these, we found at least one pair. And in most cases, we had some numbers left over. Okay, we'll deal with that in a minute. So here's the deal. If we wanted to come up with the square root of 50, okay, we would not get a clean answer for this because, yeah, we have a pair, but there's a factor left over. But here's the thing. You can calculate the square root of a pair of 5s. Okay? What one number, Brianna, here's the question. What one number would be the square root of a pair of 5s? What one number? No, not 2. What number did you pair up?
Oh, 5.
A 5. So the idea is, yeah, if you did the square root of 16, because 2 4s make it up, the root would be a single 4. Okay, so here's how this would simplify, Brian. Watch. That number that you matched up, the 5, would be a whole number 5, just like this. But where does this 2 go? It didn't get a match. So where would you still see this 2? See it here. It's going to stay behind under the radical sign. Okay, so the square root of 50 would be the same would give you the same calculation as 5 times the square root of 2.
I found the question.
Oh God, here we go.
I'm actually in the thing. Oh no. So here's the question.
She's talking about the impossible
square
quiz.
root of onion.
All right, what's it say the answer is?
Shallots?
It was shallots.
Huh?
I don't get how that works, but
the answer is really big.
No, wait.
Really big.
The square. Okay, an onion is a root vegetable, and the square-shaped root of an onion likely is a shallot. I get it now.
Huh?
They're talking about the physical makeup of the vegetable. Never mind. Okay, so all right, let's finish this off, Brianna. 5 times the square root of 2. That's equivalent to the square root of 50. And just to prove it, we'll just show it in the calculator real fast. Square root of 50, as you see it in the calculator, you see it comes out to about 7.07. If I change that and write it as 5 times the square root of 2, and there's the exact same thing. So there's proves the simplifying works. Okay. Now how about in this one, Brianna? In the square root, if I were trying to simplify radical 54, okay? Look at the pairs that we got, Brianna. Look at the pairs here. What number comes outside of the radical? What number did you pair up?
The 3.
The 3. So 3 comes out. Now, What about, now what happens here? Here you've got 2 leftovers, Brianna, a 2 and a 3. What do I do with them to determine what number stays behind? What operation do I do to the 2 and the 3? No, you don't subtract. How did you get 2 and 3 in the first place?
Oh, you multiplied them.
Well, you factored through division to split them apart. So now if you're going to put them back together, you got to multiply them. And 2 times 3 would give you
6.
Okay, so that goes there. So 3 radical 6 is the same as radical 54. All right. Now what about this one, radical 48, Brianna? Take a look at this one. Okay. This time you've got 2 pairs. You got a pair of 2's here and a pair of 2's here. Now, if this was the only one, what number would you put on the outside?
3.
No, wait. If this was the only pair, what number would you put on the outside?
The 2.
The 2. And same thing with this one. You would put what number on the outside?
The 3.
No, there's no pair of 3's there.
The 2.
The 2's. But since you have more than one pair, they both come out. So this comes out as a single 2. This comes out as a single 2. And combined, those make what?
4.
They make 4. And what's left behind? This 3 that had no match. Okay, so 4 times radical 3, the same as radical 48. And then what about in this one, Brianna, with the square root of x? Sorry. See, I bump things too.
Oh, no.
Don't mind me. Oh, chill. All right, so Brianna, now what about in the 144? We got quite a few pairs on that one. Okay, take a look. What pairs do I? How many total pairs did I come out with here?
3.
There were 3 pairs. There's a 2, there's another 2, and there's a 3. So that means you've got 2 times 2 times 3, bringing all those out. And okay, put those all together, Brianna, and multiply all those together that are coming out, and what number comes to the outside? 2 times 2 times 3 would give you?
2 times 2. 24.
Wait, try that again.
Wait, 2 times 2 is 4.
And
12.
that times the 3.
12.
12. So you get 12 there. And now here's my and now
because I did the 2 times 2 and also the 2.
you did 3 2's instead of 2 2's. All right, but wait. Now here's my other question though. Here's my other question. Were there any factors left over?
Yes. 3 and 2.
Where?
Yes. Oh.
Over here. Were there any factors left over?
No.
No. So that means, is there any radical?
No.
No. It's a whole 12. That means that 144 was a perfect square because it came out to a clean, rational answer and nothing else. Okay.
I would draw a perfect square, but then again, I can't.
No, I get what you're saying here. Okay, but the whole idea is with these radicals, when you're looking for the idea is when you're trying to simplify a radical and try to see what part of it you could draw out. The goal is to always look for pairs, and then from there, Brianna.
Yeah.
Okay.
Yeah.
The whole idea is once you found your pairs, or as I like to call them, your couples. I like to think of the radical as the house that people are living in, and when it comes time to simplify a radical, it's date night. The couples go out, the singles stay home.
That's funny.
That's how it works. Yeah. So the couples meaning anytime you have 2 of the same factor, they go out on the date night. If more than one couple goes out, then that's fine, and you get a combined product of all the couples that are going out together. And any singles, anything with no match, they stay at home. And if you have more than one, then you recombine them and stuff like that. And that's an easy way to stress the simplification, okay? And it also helps you in remembering as to which way each number goes between the couples and the singles. So look at it from that perspective. Couples go out, singles stay home. And that's it. And you know what? That's going to do it for us here, because I think we've done everything possible, at least for the moment, regarding trees that we possibly can here. I think this is genuinely the first themed live stream that we've ever done here. I don't know if we can possibly do something like that again, but heaven knows if we can find a way and just be inventive, what the heck, we'll do it. And now I'm alone because Brianna left the room to get something. Where did she disappear to? There you are. Okay,
Wait,
yes, get over here. We got.
Something?
All right, real quick, because we got to sign off here. Because while she's getting it, I'll go through the usual spiel. Okay, like I said, go to the front page or go right below this video. Click the thumbs up if you enjoyed it, all the comedy and math and zaniness that we did here, whatever, and hit that subscribe button, hit that notification bell so you know when we're doing our next streams. And I swear we got videos coming. Okay, things have just been a bit more busier than I thought they've been, but I promise I'm working on while I'm catching up my other stuff. You will be seeing new videos from us very, very soon. Okay, I swear it. Okay, so you do that and tell everybody else that needs help and stuff like that. Even as the circumstances regarding business around the country changes, we will still be here as long as I am stuck here. So just enjoy it. All right. Before we go, last item. Okay.
I have some rocks I would like to show everyone. Wait, I need to get one more.
Brianna, come on, we gotta move.
Okay, here it is. Okay, so this is Pet Rock. This is Pet Rock. And then I made a bunch of Steven Universe themed rocks. I'm still.
What did I tell you guys about?
I think 2 more.
Three more.
Not
getting
3.
Limiting your personal content here and stuff like that. But that's okay. You're here now. Go ahead.
I made amethyst, armrest.
Leave it alone. I'm not.
Ruby and sapphire. And
Ruby and
together garnet.
Ruby and sapphire, yeah, who together are garnet, which would be this one, right?
No, that's pearl or Squidward.
Oh, stop it!
This is
another reference to Jello Apocalypse's
This is supposed to be
thing.
Steven.
Oh, who is the embodiment of rose quartz?
Yeah, but that's why I'm also making pink diamonds, which spoiler alert.
The series is over. If they haven't seen it by now.
Rose quartz is pink diamonds, and I didn't just want to make another one of these because, like, it doesn't make sense. Peridot.
That's how you say it.
Peridot.
You pronounce it's a long O and the T is silent. That's how you say the name of the gem.
No, but in the series it's called Peridot.
Okay, sure.
And lapis. And I'm making bismuth, jasper, and pink diamond, aka rose quartz. I didn't just want to make another gem that looks like Steven.
Exactly. Yeah. So
They're
that's how they've been keeping. That's how they've been keeping themselves busy these days. They've been painting rocks here. Well, here you go paint more rocks and finish the rest of your work today. We're gonna let you guys finish the rest of your work or whatever. Okay, and
wait,
please keep sending us more topics that you want us to do in these live streams.
Can a match box? Can a match box?
I forget how this finishes.
Dad. Here,
I forget the rest of it. Oh boy.
Okay.
She never ceases to amaze. She gets getting too much of her stuff in. We'll see you guys. We'll see you guys soon. All right, go. Come on.
Want to know the answer?
Finish. Yes.
No, but a tin can.
That's what it was. Okay.
Can a matchbox?
Yes. I forgot what it was. All right. We'll see you guys Friday at 2 p.m.
Bye.
here for more math funs. Okay. And more games. Don't forget, we will do games. We will come up with more games every Friday. For now, see you soon. Take care, gang.
We ended it with a bang.
So be it.